Welcome to This Explainer. Today, we're diving straight into the hidden architecture of the internet to reveal the absolute magic happening right behind your screen. I mean, have you ever really stopped to think about what is actually going on when you browse the web, send an email, or stream a movie?
It's a question we almost never ask, right? But the very second you click a link, an incredibly complex journey begins. You're essentially setting off a chain reaction that spans across copper wires, fiber optic cables, and radio waves, instantly connecting your specific device to servers that could literally be sitting on another continent. When you look at the sheer, unfathomable scale of the global internet, we're talking billions of end systems, millions of packet switches, countless miles of physical media. You really have to wonder how on earth we organize all this chaos into a reliable system. How is it that your data doesn't just get lost in the noise? The answer? Well, it's a brilliantly organized, completely hidden architecture. Here is our roadmap for today. We'll start with the internet's hidden structure, move into the rules of communication, break down the 5-layer protocol stack, hit our big aha moment with encapsulation, and finally, we'll see the whole stack in action. All right, let's jump right into the first piece of the puzzle, the internet's hidden structure. To handle literally billions of devices and links without crashing, network designers organize the hardware and software into specific, manageable layers. A really great way to think about this is to imagine the airline system. The airline industry is massively complex, but it relies on layers, right? You've got a layer for ticketing, one for baggage checking, another for gate management, and one for flight routing. And just like the airlines, well, mostly, each layer performs a specific function and relies heavily on the layer right below it. By structuring the internet in that exact same way, we can take a staggering global infrastructure and make it functional, modular, and upgradable.
But before we can stack those layers, we need to talk about part 2, the rules of communication.
Here's the deal. All activity on the internet is governed by what we call a protocol. Whether it's your laptop connecting to a Wi-Fi router or a massive data center talking to a backbone switch, they aren't just firing random voltages back and forth at each other. They're speaking a highly specific, standardized language. A protocol dictates exactly how a message should be formatted, the sequence in which messages should be sent, and what to do when a message is actually received. It's actually pretty similar to human interaction. Say I ask you, hey, what time is it? I expect you to hear me, process that request, and reply with the time. If you reply by, handing me an apple, well, the protocol has completely broken down. In a network protocol, these messages and expected actions are just executed by hardware or software exchanging specifically formatted bits of data. Now that we know the rules, let's look at part 3, the 5-layer protocol stack. This stack is built in 5 distinct steps. Up at the very top is the application layer. This is what you interact with directly, like your web browser. Moving down, the transport layer handles process-to-process delivery. Below that, the network layer routes your data across the globe. Then, the link layer moves data across a single direct connection. And finally, sitting at the bottom is the physical layer, transmitting raw zeros and ones across copper wires and radio waves. The real beauty of this layered architecture is that each step has one highly dedicated job, keeping the overall complexity completely isolated. Your web browser, which is operating up at the application layer, doesn't need to know if you're connected via coffee shop Wi-Fi, a 5G cellular network, or a wired Ethernet cable at your desk. It simply hands the data down to the transport layer and basically says, here, you deal with this. Each layer provides a service to the layer directly above it, while relying completely on the services of the layer directly below it. Which brings us to part 4. This is the core of our explainer, and honestly, the real aha moment, encapsulation. To understand how data actually travels down this 5-layer stack, I want you to imagine your data is a simple inter-office memo that needs to travel from someone in one branch of a company to a very specific person in another branch all the way across the country. Let's map this analogy onto the actual technical terms. At the application layer, your raw data is called a message. Think of this as the original written memo. When it drops down to the transport layer, it becomes a segment. This is like slipping the memo into a yellow inter-office envelope with the recipient's name and department jotted on the front. Next, it moves to the network layer and becomes a datagram. This is like taking that yellow envelope and putting it inside a standard stamped postal envelope with a global street address on it. Finally, at the link layer, it becomes a frame. That's the mail truck that physically drives the envelope from the post office to the next sorting facility down the road. This perfectly illustrates the concept of encapsulation. It works exactly like a Russian nesting doll. Each layer adds its own specific header or envelope around the original message from the layer above it. Now, while the network layer is busy figuring out how to route your nested envelopes through the massive postal system of the internet, the transport layer has a much more intimate job. It acts just like the specific mailroom clerks inside those offices. When the transport layer receives data, it ensures it gets to the exact right application process. For example, making sure your incoming email data doesn't accidentally get sent to your web browser. We call this process demultiplexing. It uses port numbers on that inner yellow envelope to make sure the right application gets the right message.
When you look at it mathematically, the process is just incredibly elegant. As your raw message is pushed down the stack, every single layer attaches a new header to the front of the payload. The transport layer slaps on its header, HT. The network layer takes that entire segment and encapsulates it in its own header, HN. Finally, the link layer wraps that datagram in its header, HL. So the payload for any given layer is quite simply the fully assembled packet from the layer directly above it.
Okay, let's bring it all together with part 5, the stack in action.
So what happens when this fully loaded frame actually hits the network? Well, here is a fascinating detail. The intermediate stops on the internet, the actual physical routers and switches moving your data, they don't open the innermost envelopes. They don't care what your memo says. Link layer switches only implement layers 1 and 2. They only read the outermost envelope to get it to the next hop. Internet routers only implement layers 1, 2, and 3. They only read up to the network layer to figure out the next geographic leap. The transport and application layers, completely invisible to the core of the network. The true intelligence of the internet is pushed all the way to the edges, to your device and the server you're talking to.
Once that frame finally arrives at its destination, the exact reverse process kicks in. We call it de-encapsulation. The receiving hardware's link layer strips off its header and hands the package up. The network layer reads its address, removes its header, and passes it along. The transport layer finds the right application port, discards its envelope, and finally, boom, the pristine original memo is handed right to your web browser.
It is absolutely mind-boggling when you think about it. Every single time you click a link or stream a video, literally millions of these invisible Russian nesting dolls are assembled, launched across the globe, and disassembled at lightning speed. It gives you a profound new appreciation for the architecture of our modern world. And honestly, it leaves you wondering, if this much invisible complexity hides behind just a simple click, what other digital miracles are happening right beneath our fingertips?